Okay, let's talk about the energy stored in a spring. So I've got my little space monster here that I'm going to push down, and that suction cup's going to hold it. At some point, it's going to pop off, and hopefully we can measure how high it jumped and actually get an estimate of the potential energy stored in the spring. So let's take a look at energy stored in a spring. Hi, and we're back with energy of a compressed spring, or maybe it's not compressed, maybe it's stretched out, but the energy stored within a spring. And so we've got this equation where U is potential energy, and the little S stands for spring, is equal to 1/2 kx squared, where k is the spring constant, and x is how much the spring is either compressed or stretched in meters. So you can have a little toy like this, where you can compress the spring and lock it in place, and it'll pop off and shoot this up in the air. And we can actually figure out a lot of things with this simple toy. So let's take a look at an example with this guy and see what we can come up with. Now, it actually jumped out of my screen. So let's say there's the little monster and there's a spring. Let's say that it jumped up so that it had a height of about 30 centimeters from where it launched at. So center of mass up to the center of mass, about 30 centimeters. Let's try to estimate the spring constant in that spring. So what can we do? Well, we know when we compressed it, it had potential energy in the spring, that compression. Okay? And when it fired off, that potential energy became kinetic energy and then became potential energy as this little monster flew up in the air. But all that potential energy stored in the spring became gravitational potential energy. So we can say gravitational potential energy is mass times gravity times height, and the potential in a spring is 1/2 kx squared. We can actually set those equal to each other because the potential energy in the spring became gravitational potential energy. So we can say that potential energy became spring potential energy and vice versa. Same way it works the other way around. If something falls on a spring, that potential energy became kinetic energy, then hit the spring and became potential energy in the spring. So it can go backwards too. So potential energy at the top could equal potential energy stored in the spring. In this case, we've got this scenario. So we've got mass times gravity times height equals 1/2 kx squared. And we can figure out what k is, because we've got the mass. Now we got grams, so we have to change that to kilograms. Gravity is 9.8. Height was 30 centimeters. We got to change that to meters, so 0.3 equals 1/2 k. The spring was compressed 1 centimeter, so 0.01, and that's squared. So at this point, let me move the monster there, we can actually calculate that. So 0.15 times 9.8 times 0.3 times 2, we're going to move that over, and divide by 0.01 squared, and we get a spring constant, wow, a spring constant of 8820 newtons per meter. That seems big, but you got to remember that's over a whole meter of compression, but we only actually compressed it about a centimeter. Okay. So let's take a look where we have kinetic energy becoming energy in a spring. Pinball was a neat game where you pulled the spring back and it compressed the spring and the ball rolled up against it. Then we let it go, the spring shot forward and the ball went flying off into the game. And so we're going to figure out the spring constant. No, we actually have the spring. We're going to figure out the velocity of the ball after it leaves the spring. So in this case, that potential energy stored in the spring will actually become kinetic energy of the ball flying off in this case. Or it could be one where the ball rolls in and hits it and compresses the spring. It could work either way, but this time we're actually firing off a spring to launch the ball. So potential energy spring is 1/2 kx squared. Kinetic energy is 1/2 mv squared. Now the cool thing is, if we write this out, the halves actually cancel out. We just left with kx squared equals mv squared. And we can do that. We've got the spring constant be 14. It is compressed 3 centimeters, so 0.03, and that's squared, equals the mass, 50 grams, so 0.05. And we want to figure out the velocity. So let's do a little plug and chug. So 0.03 squared times 14 equals, divide by 0.05. And then we got to take the square root of that. And so this ball comes off with a speed of about half a meter per second. It seems a little bit slow. We probably should have had a higher spring constant because I'm pretty sure they come off faster than that. But that gives you a good example of how this works. Okay? Thank you, and I'll talk to you later with another video.